Yeah, welcome to the next seminar. Today we're very pleased to have Dr. Mingyu visiting us from Princeton GFDL. So Mingyu originally came from Korea. He did his undergraduate at Seoul National University, and then joined Penn State. And as a PhD student, he got his PhD and then moved to Princeton GFDL at the beginning of last year, I think 2022, and joined the seasonal to decadal predictability Brook. And he's working there with sort of a GFDL scholarship fellowship there. So today he's going to talk about on the causes of synoptic-scale eddy heat flux decline. So again, after the seminar, we'll have lunch over at Challenger, and then students will be meeting with him after lunch. Yeah.
Thanks, Dr. Edmund Chang, for a nice introduction. Hi, everyone. My name is Mingyu Park, and I'm a postdoc in Princeton University, and also in the Seasonal to Decadal Variability and Predictability Division in NOAA GFDL. So it is my honor to give a talk today at Stony Brook University. I'm going to talk about on the causes of synoptic-scale at the heat flux decline. And I'd like to acknowledge Dr. Soo-Kyung Lee in Penn State University for collaboration and advising those studies. Okay, so before jumping into actual research presentation, I want to briefly introduce about myself. So my research background is large-scale dynamics, and more specifically, atmospheric teleconnection. And one of the important formation mechanism of the atmospheric teleconnection is planetary waves generated by tropical convection. So Rossby waves are mostly often trapped in the tropical estuaries based on the linear Rossby wave theory. But previous studies in the 1980s also showed that Rossby waves can propagate out of the tropics in certain conditions. For example, if there is anomalous divergent wind induced by tropical convection, which attracts absolute vorticity out of the tropics, or if there is strong subtropical divergence or convergence near the subtropical jet region, and then we can see forward propagating this large scale waves and make a atmospheric teleconnection pattern, acting as Rossby wave source. So with this, from this perspective, with my advisor Soo-Kyung, we worked on how this mechanism can be used to understand teleconnection driven Arctic warming. And we actually showed that this teleconnection driven Arctic warming mechanism can be useful for understanding the current warm Arctic cold continent pattern, which is well observed in the recent period on the intraseasonal time scale. Using this mechanism, we also worked on how this mechanism can be used to understand the growth of planetary-scale eddies driven by tropical convection can result in this midwinter minimum, midwinter suppression of the extratropical storm tracks, which is a long-standing research question in the storm track community. And we also showed that this mechanism, this planetary waves excited from localized tropical convection, can be root cause of this extratropical circulation biases in the state-of-the-art climate models. And last year, we also worked on how this mechanism can be used to understand the intraseasonal variability of planetary scale and synoptic scale at heat fluxes. And they are actually related with this current decreasing trend of the synoptic scale at the heat flux. And so today's talk will be mostly about these highlighted studies. Okay, let's start from the title of this talk. The title is On the Causes of Synoptic-Scale Eddy Flux Decline, and I underlined 3 keywords in the title. So what do I mean by synoptic scale? So according to the AMS glossary, synoptic scale refers to sizes of weather systems ranging from several hundred kilometers to several thousand kilometers, and also the scale of migratory high and low pressure systems of the lower troposphere. So in atmospheric large-scale dynamics, depending on one's interests, you can define synoptic scale in several different ways. But in this talk, we define the synoptic scale as the spatial scale of circulation anomalies that is has zonal wave number equal to or larger than 4. And the second keyword is Eddy. So in studies of the general circulation, the departures of a field from the zonal mean of that field is defined as eddies. So if I say eddy temperature or eddy vorticity field, then it indicates zonally varying deviations of temperature or vorticity in the atmospheric field respectively. And the last keyword is heat flux. So it is pretty straightforward, the definition of heat flux is. So it indicates the rate of flow, heat, or temperature. So in this talk, I'll define this heat flux as meridional transport of temperature, or sometimes it is defined as a meridional transport of sensible heat. So putting these all 3 keywords together, I'm going to talk about meridional transport of sensible heat or temperature that has sizes of daily weather systems and also zonally varying that has zonally varying deviations. Okay, so why do we care about atmospheric energy heat transport? So the figure shows here is the net annual radiation budget picture. And in textbook type explanation, there's a net surplus of incoming solar radiation in the tropics, and there's a net deficit in mid latitudes and high latitudes. So this radiative imbalance is important, and atmospheric energy heat transport actually plays an important role in alleviating this radiative imbalance of the Earth. So this radiation imbalance necessitates the heat transport from the tropics to the polar region through ocean and the atmosphere, and thus drives the general circulation in the atmosphere. So we can decompose this total atmospheric energy transport into latent moist heat part and dry sensible heat part. And the dry sensible energy heat transport is mostly driven by this temperature, meridional temperature fluxes. So the figure on the right shows the total this eddy heat flux, total eddy meridional eddy heat transport, and the middle 2 panels shows the contribution from transient eddies and the stationary eddies. Let's forget about what transient and stationary mean here. And the bottom panel shows the contribution from mean circulation. And as you can see from these line plots, this atmospheric heat transports are mostly driven by eddies rather than mean circulation. So atmospheric eddy heat transport is very important for alleviating this radiative imbalance. Okay, then is that only reason? I would say no. So meridional eddy heat flux is actually a very important physical process, not only for global energy imbalance, but also for internal atmospheric dynamics, such as storm track dynamics or tropospheric stratosphere coupling. So the figure on the left shows a storm track dynamics example. So the meridional eddy heat flux is involved in this baroclinic eddy conversion that fuels storm track eddies. So storm track eddies are very important for precipitation and the temperature variability in mid latitudes. So we can infer that meridional eddy flux is important. And also for the tropospheric and stratospheric coupling, this meridional eddy heat flux is an important metric of upward wave activity that perturbs stratospheric circulation. So I would say meridional eddy heat fluxes are very important, not only for global energy balance, but also for this internal dynamics. Okay, then why is the trend of meridional eddy heat flux important? Of course, there might be several reasons, especially if we link this to the high greenhouse gas emission scenario. But I will answer that a long-term variation of meridional eddy heat flux is also linked to changes in many atmospheric and climate variability. So for example, the figure on the left shows the SIMI-5 climate model results in the future Arctic warming and the future tropical warming. So basically, they calculated the contribution of the climate feedbacks to Arctic warming and tropical warming in the future. And the role of atmospheric dry sensible heat transport in the future Arctic warming is negative. So this atmospheric heat transport actually alleviates Arctic warming in some sense in the future. So this kind of understanding the trend can help how climate response will be in the future projection. So I'll say for that reason, this is very important. Okay, so in literature, eddy heat flux variability is understood by using the flux gradient relationship, simple flux gradient relationship. So in other words, eddy heat flux is proportional to minus d times dt dy, and this large character d refers to eddy diffusivity, and it's related to the intrinsic eddy's characteristics. And I want to say there's entirely separate, rich literature of theoretical studies about this eddy diffusivity, but I will not discuss this in this talk because assuming that this eddy diffusivity has negligible trend in the future. So it's mostly about this dt dy or equal to temperature gradient. So coming back to this energy imbalance picture, from the flux gradient relationship, the baroclinic eddy heat flux is expected to decrease as the equator per temperature gradient decreases. So you might have heard of Arctic amplification. So Arctic warming is faster than rest of the globe. So actually that means the equator per temperature meridional gradient will decrease and decrease more in the future. So from this flux gradient relationship, it's pretty obvious that eddy heat flux is expected to decrease. And indeed, that's what's happening now and expected to happen in the future. So the figure here is from Chemiki and Provani. So they used very different, very diverse climate models, and also a single climate model simulation with different initial conditions, which is termed as large ensemble here. And they also used 4 different reanalysis data set for the robustness of their results. And the results shown here are changes in annual Northern Hemisphere lower tropospheric eddy heat flux over the recent 4 decades relative to the base period, 1979 to 1989. So it is pretty obvious to see that these green colors representing this observational products are decreasing as time goes by. And the black solid line here is large ensemble with fixed greenhouse gas. And you can see that eddy heat flux with fixed greenhouse gas scenario is actually nearly constant. So they attribute this eddy heat flux decline to greenhouse gas forcing. So it's a forced response of this eddy heat flux decline that we expected to have in the future. However, I want to note that there is also seasonality in Arctic warming. So namely, Arctic warming is the largest during boreal winter and smallest during boreal summer. So I want to raise this question. What is the month-to-month trend of synoptic scale eddy heat flux over the recent few decades? So to address this question, I basically computed eddy heat fluxes. So eddy heat flux is defined as V star theta star bar, where bar indicates zonal mean and asterisk indicates deviation therefrom. And eddy heat fluxes are also separately calculated for planetary and synoptic scale eddy components. So planetary scale, I define in this study zonal wave number 1 to 3, very large scale, more than 10,000 kilometers in mid latitude, and synoptic scale, as I introduced earlier. And also Eddy heat fluxes are computed for 6-hourly time steps and then daily average. And ERA5 reanalysis data is used for the period of 1979 to 2019. I also used JRA55 reanalysis data set, and the results are qualitatively consistent. And moreover, I want to note before I present results that if I use different definition of synoptic scale at the heat flux by using the time dimension filter. So in other words, if I define synoptic scale at the heat flux as 10-day high pass filtered at the heat flux, then still the conclusion that I will show is remains the same. Yeah, and also low pass filter for planetary scale at the heat flux. And next, I define equal temperature gradient by using the second Legendre polynomial coefficient. So, so this gradient is 1.5 times the second Legendre polynomial coefficient, and that is representing this higher latitude and lower latitude temperature difference. Previous studies found that the second Legendre polynomial, which are so Legendre polynomials are orthogonal basis functions like Fourier harmonics, and they found the second Legendre polynomial is morphologically similar to this equal to pore temperature gradient. So it can be used to represent latitudinal temperature variations rather than using the simple temperature different domain average temperature difference. I'll discuss it more in the later slides. So I use this Legendre polynomial expansion to daily temperature, and then I derive daily coefficient of this second Legendre polynomial, and then I basically constructed the index by removing its seasonal cycle and then normalized by its standard deviation. Yeah. So in short, I constructed a way to measure this daily variability of this equal to temperature gradient. Okay, so here's a result. This is monthly trends of synoptic scale at the heat flux averaged over the 40 to 70 north latitudinal band, because that's where synoptic scale eddies are mostly developed. And the x-axis shows different months from January to December, and the y-axis represents the pressure level. So consistent with previous study, in the annual mean, if you do annual mean by eyeballing, the Eddy heat fluxes are decreasing. But there are much more than that. Month-to-month variability is pretty large. So if you focus on this March, for example, there's actually increasing synoptic scale at the heat flux trend. And during summer, it's relatively weak. Okay, then what about equal to pore temperature gradient? Does it have similar variability as synoptic scale at the heat flux does? And it turns out mostly equal to pore temperature gradients are decreasing statistically significantly. But there are two additional notes I want to mention. So first one, March, is actually very substantially decreasing. So it's a bit different from what synoptic scale at the heat flux increase says. And also in July, consistent with weaker Arctic amplification I mentioned before, Arctic warming is the smallest during boreal summer. This trend is also pretty weak compared to other months. So in this aspect, I also want to make another argument that synoptic high frequency eddy heat fluxes are compensated by planetary scale low frequency eddy heat fluxes during boreal winter. So March is kind of boreal winter months, and there might be a possibility that rather than equal to pore temperature gradient, large scale, this planetary scale eddy heat fluxes might be more important for this declining synoptic scale eddy heat flux. So I additionally asked the question, what is the trend of then planetary scale eddy heat flux over the recent 2 decades? Well, it turns out monthly trends of planetary scale eddy heat flux are more complicated than synoptic scale eddy heat flux. We see this positive, negative signals. but there are some general tendency. So in general, planet-scale Eddy heat fluxes, the trends are large. The magnitudes are large during winter months and relatively weak in summer months. And also in March, there's a significantly decreasing planet-scale Eddy heat flux trend. So suggesting that for winter months at least, the relationship between planet-scale Eddy heat flux or PF and SF, synoptic-scale Eddy heat flux, might be more important than the SF and equilibrium temperature gradient relationship. Okay, so that was a kind of introduction. So going back to the synoptic-scale Eddy heat flux trends map. So in this talk, I'll talk about what causes synoptic-scale Eddy heat flux decline during boreal summer and boreal winter in part 1 and part 2 respectively.
Yeah, I have a question.
Yes.
Here. So if you back to your previous figure,
yeah,
seems that things are pretty noisy.
Yes.
Here.
Yes.
So are these systematic change or are those just climate variability, or how do you sort of separate it? Because it seems that different months actually do things differently. So
yeah, different. Yeah, that's true. It's more noisy, but so after going over this month-to-month variability, we rather focus on seasonal Eddy heat flux trends. So in general, keep saying in general. So if we average DJF, then there's more increasing planet-scale Eddy heat flux trend. And for summer, it's more muted. It's more weak. So we do not pay attention to summer season planet-scale Eddy heat flux trends. Of course, yeah, I agree that there's month-to-month variability very large in planet-scale Eddy heat flux here. So it's hard to derive meaningful conclusion from this map only. So from now on, I'll focus on more seasonal time scale. So it was kind of motivation to separate summertime and the wintertime synoptic-scale Eddy heat flux decline, rather than month-to-month based analysis. Thanks for a good question. Okay, so part 1 is boreal summer. And what process drives the declining trend of synoptic-scale Eddy heat flux during boreal summer is the research question I have. And this is the results I'm presenting is based on the paper published last December on the causes of synoptic-scale Eddy flux decline. Okay, so from observational analysis in atmospheric dynamics, people often draw this causal relationship by using the lag composite analysis. And to do that, for this purpose, we also constructed an index to measure the similarity between the daily SF synoptic-scale Eddy heat flux anomaly field and each recent declining trend pattern over mid-latitude troposphere. So by using the projection method. So let's say if synoptic-scale Eddy heat flux in mid-latitude is decreasing, then if it's overlaid onto its trend pattern, the multiplication of those two gives you positive value. So based on this positive value, those values of daily time series, we can make an index. So positive synoptic-scale Eddy heat flux trend index, or SFI, means that synoptic-scale Eddy heat flux is decreasing in mid-latitude troposphere on the daily time scale. And because of the linearity in this projection method, if the SFI index has negative values, then it shows the increasing SF or synoptic-scale Eddy heat fluxes in mid-latitudes. Okay, so before presenting the lag composite analysis results, I want to additionally note that there is a high latitude warming on the interdecadal timescale during boreal summer, and it's mostly driven by land warming. So the focus here is land warming. The figure here shows the June, July, August trend over the recent 4 decades, and the variable shown here is a skin temperature, surface temperature. And we see this large yellow signals all over the world, but if we look at closely, it's more concentrated to high latitude lands compared to lower latitudes. And it's mostly focused on concentrated over land rather than ocean. And during boreal summer, Arctic Ocean has more open water. So obviously, ocean has much more larger heat capacity. So the skin temperature trend is relatively small compared to land. And the reason I mentioned here is that consistent with this interdecadal analysis, intraseasonal analysis shows a similar results. So these are composites of skin temperature anomalies during SFI, positive SFI events. The figure here shows the geographical map at leg days -7 to -3, basically 1 week prior. And the right panel here shows zonal mean. And we can see that before eddy heat fluxes, synoptic eddy heat fluxes decline in mid latitudes, there's a large land warming or high latitude land warming concentrated. So it combined with the mid latitude cooling, there's a local meridional temperature gradient decrease. So in the next pentad, we see this increased zonal mean picture. This zonal mean signal is mostly deteriorated, corresponding to synoptic scale at heat flux decline. Okay, so then a question that naturally follows is that what physical process drives this land warming? So to address this question, we use the surface energy budget analysis over land to find the dominant physical process. So let's assume this infinitesimally thin storage layer. So lands do not store the heat or temperature much. Then this assumption gives you left-hand side the storage term 0. And this is the right-hand side is largely balanced between the radiation terms and the surface heat flux terms and the residual. So more specifically, the right-hand side, downward shortwave radiation plus upward shortwave radiation and downward long wave, upward long wave, and sensible heat, latent heat fluxes, and the residual, which is mostly including ground flux. So among these terms, we are trying to find which one is the most dominant. So the figure here shows the same skin temperature anomaly field that I showed in the previous slide, but now it's zonal mean. And the x-axis is now lag days. So lag day -10 to 0 to +10. And the y-axis here is now latitude. So we see that higher latitude land warming precedes this green dashed synoptic scale eddy heat fluxes. And also there's a middle latitude cooling. So both precondition this synoptic scale eddy heat flux decline. And it turned out it's mostly downward shortwave radiation that drives this skin temperature anomalies. So black contour here is the skin temperature overlaid. And we see that the net solar radiation matches and has also large magnitudes before synoptic scale eddy heat flux declines. And compared to that, surface downward thermal radiation, downward long wave radiation also contributes to positive temperature anomalies a bit, but it's mostly at positive lengths. And that means that this downward radiation anomalies are rather arise in response to the reduction of synoptic scale eddy heat flux. So it's not main driver, it's likely to be response. Okay, then what about other terms? What about surface heat flux terms? Then it turns out we also looked at surface sensible heat flux and surface latent heat flux, and they show small contribution over land for the skin temperature anomalies. So we conclude that downward shortwave radiation, solar radiation is the most important physical process, at least for this composite synoptic scale eddy heat flux decline. Okay, so now we are trying to generalize this relationship. So we want to address the relationship between mid-latitude synoptic scale eddy heat flux and high-latitude land warming by using regression method. But before that, let me show the relationship between mid-latitude SF and the equator temperature gradient, the polynomial-based TY index. And if we see these regression coefficients, x-axis is a zonal wave number and y-axis is a latitude. We see that Synoptic-Scale zonal wave number Eddy heat fluxes has negative regressions compared to against equator temperature gradient, which is what I repeatedly mentioned in mid-latitude. So if we compare this with the high latitude landwarming regression, so the right panel now shows that I regressed the high latitude landwarming temperature variability against this Eddy heat flux at each zonal wave number. Then we see much larger negative regressions. So we kind of narrow down equator temperature gradient is an important culprit, but we narrow down high latitude landwarming as a more important driver of this Synoptic-Scale Eddy heat flux decline. And it turned out equator temperature gradient, this index is also related to high latitude landwarming. So they are not independent of each other. The equator temperature gradient index captures high latitude landwarming. So the panel here on the left shows the top enhanced equator temperature gradient in 50 days. The variable shown here is 2-meter surface temperature anomalies. And we see that the temperature signals are mostly over the land region. It's over Eurasia and North America. And on the other hand, if the equator temperature gradient is suppressed, means high latitude is largely warmed, then it's also mostly from land area. Okay, so this kind of supports that high latitude landwarming is important. Then some of you might have wondered why this second Legendre polynomial based index is useful. Why do you use that? It's complicated. There are more simple metrics that previous studies used. So to address that question and to address the merit of using this second Legendre polynomial to define the equator temperature gradient, so the figure here shows what previous studies used to measure the equator temperature gradient. They just simply averaged some kind of lower latitude domain and then high latitude domain, and then subtract them and you can show the differences between them. So for example, Harvey et al. 2014 paper, they defined 30 south to 30 north as lower latitudes and 16 to 90 north as high latitude. And the landwarming captured by this metric is 1.14 Kelvin, whereas Chemeki and Provani 2020 study used 20 to 40 north lower latitudes and defined high latitude as 65 to 85 north, and that metric captures landwarming 0.72 Kelvin. So there are some ranges. Well, what about our second Legendre polynomial based index? It captures 1.53 Kelvin for landwarming. And the domain metric methodology captures landwarming ranges from 0.7 Kelvin to 1.38 Kelvin. So it has large ranges. So our TY index not only captures landwarming more effectively, but also we do not have to make an arbitrary choice of domains, how to define tropics, how to define polar regions. So with those merits, we use this the polynomial in this study, and the results are also turned out to be pretty clean. Okay, so with these results in part 1, I want to highlight that global landwarming, not only high latitude, but global landwarming in general is much more faster than global warming or ocean warming. So the figure here shows the global average surface temperature change from pre-industrial period, which is regularly updated by my colleague Zachary Leib in GFDL. It's regularly updated in his website. We see that up to January 2023, landwarming is skyrocketing since the 1970s, much more than ocean and global warming. So I want to point out that this landwarming, global landwarming, is not only impactful in Synoptic-Scale Eddy heat flux, but also in hydroclimates globally. So it'll be we should pay attention to this increase. I'd like to argue. Okay, so the takeaways of part one, for time constraint, I'll briefly mention. So synoptic-scale Eddy heat flux declines corresponding to decreasing meridional temperature gradient. And I mentioned it is high latitude land warming due to shortwave radiation that contributes to this meridional temperature gradient trend. Okay, now I switch my gear to part two, the boreal winter now. So what process drives the declining trend of synoptic scale and heat flux during boreal winter? And the results are also from my earlier 2022 study published in Journal of the Atmospheric Science. This research has been prompted by previous climate modeling studies who paid attention to the future changes in the thermal structure of Northern Hemisphere troposphere. So the figure here is the ensemble signified ensemble mean, zonal mean temperature trend from the 1% CO2 increase per year scenario. And what's shown here is that from this yellow arrow, upper tropospheric, this tropical warming is much more larger than the polar region. So there is an increase in baroclinicity or increasing trend of the equator temperature gradient in upper troposphere. However, when it comes to the near the surface, because of Arctic amplification, larger polar warming, there is a decreased baroclinicity at the surface expected in the future. So there is a thermodynamic tug of war in future climate. And the climate response in question is realized through baroclinic eddies that respond to these meridional temperature gradients. Then an overarching research question is which meridional temperature gradient is more dominant in driving this climate response? Is it upper troposphere or is it near surface equator temperature gradient? So previous employing this idealized modeling framework, previous studies already attempted to address this question: what would be Eddy response to meridional temperature gradients? So this recent modeling study, Yuval and Caspi 2016, showed that they forced this dry idealized models with the equal increase of baroclinic or equal degree of equal temperature gradient increase at 3 different levels. So upper level and the mid troposphere and the lower troposphere. And the figure here shows the Eddy heat flux response to this perturbed meridional temperature gradient. And they found that actually upper troposphere results in more larger Eddy heat flux increase if the gradient is increased compared to this smaller increase of at the lower troposphere when the model is perturbed at the lower troposphere. But these model results are diverging depending on the model setup. So we want to show observational evidence of this question, which is more effective driving this Eddy heat flux variability. There's another source of this Eddy heat flux, which is zonally asymmetric tropical convective heating. So many previous studies show that forward heat transport can be driven by eddies excited from localized tropical convection that I introduced at the beginning. For instance, this Bagan and Lee 2015 showed that if there's a localized tropical convection over the western tropical Pacific, then a week later they see this large growth of planetary-scale eddies, Eddy heat flux over high latitudes. So now the research objectives are investigating the relationship between Eddy heat fluxes and surface equator temperature gradient, upper level gradient, and zonal asymmetry in tropical convective heating. And we additionally use JR55 for convective heating index. So our Legendre polynomial index captures this variability of equator temperature gradient very well. So the top panels show the surface equator temperature gradient index, and you see it's mostly Arctic warming, near surface Arctic warming drives this variability of baroclinicity. And the upper level temperature gradient is not only this Arctic cooling, but also this upper tropospheric tropical warming or cooling that drives the variability of this upper troposphere meridional temperature gradient. So what I want to say is our indices capture this variability reasonably well. And our index of this zonal asymmetry of tropical convective heating also captures well this observed variability. So if QX index is large, then there's warming or heating over Western tropical Pacific, cooling over Central tropical Pacific. So if you think about zonal gradients, they are increasing, and vice versa for the negative Q index. Okay, so our three indices are well constructed. Then I want to investigate the intraseasonal variability or relationship between these Eddy heat fluxes, both planetary scale and synoptic scale, with these three different indices. So the figure shown here is a regression map at three different legs. So leg day -7, negative leg day 0, and the leg day +7. And the x-axis is a latitude from equator to pole, and the y-axis is pressure. And in the first row, so we regressed surface temperature gradient index against plant scale at the heat flux. And as you can see here, there's a large negative regressions at leg -7. And it means that changes in surface temperature gradients are largely regulated by plant scale at the heat fluxes. So in other words, if plant scale at the heat flux is enhanced, prior to equator temperature, I'm sorry. So if plant scale heat fluxes are increased and enhanced, then there's Arctic warming, which decreases the surface equator temperature gradient. So there is a negative regression. And when it comes to the enhanced upper level temperature gradient at the enhanced upper level temperature gradient, and it leads to a large enhancement of plant scale Eddy heat flux over the exotropics in positive leg. So it means that the now driver is the equator temperature gradient at upper level. It's not response, it's driver of plant scale Eddy heat flux. So it's completely opposite to surface equator temperature gradient relationship. And the third row shows that the zonal asymmetry of tropical convective heating leads this plant scale Eddy heat flux enhancement over the exotropics. And that's represented by large regressions at positive legs. So if positive leg has large regression, then it means the index leads the Eddy heat flux variability. So hope that causality is clear. Then what about synoptic scale Eddy heat flux? So we did same regression map, but against synoptic scale Eddy heat fluxes. So again, the first row is surface temperature gradient. And we see that the regression coefficients are large at leg day 0 and leg day 7, positive legs. And it means that surface temperature gradients are now driver of synoptic scale Eddy heat flux anomalies. So if surface temperature gradients are increased by Arctic cooling, then synoptic scale Eddy heat fluxes are expected to grow more vigorously. Then when it comes to enhanced upper level temperature gradient, that also leads to synoptic scale SF growth, synoptic scale Eddy heat flux growth, but to a weaker extent than the surface temperature gradient. And it also has large negative regression at negative legs. And now the third row is tropical convective heating variability. And we basically see the muted response. There's not much relationship between zonal asymmetry of tropical convective heating and the synoptic scale of the heat flux directly. Okay, so now we are close to the end. To quantitatively compare these regression coefficients, now we did computed leg time series of regression coefficient between Eddy heat fluxes. Now Eddy heat fluxes are domain average, 30 to 80 north and 300 to 1000 hectopascal to represent the middle latitude extratropical troposphere, and the coefficient between the indices. So it's hard to see here, but the point I want to mention is the panel A here shows the relationship between PF and the surface equator temperature gradient, and they have large negative regression at negative legs. So PF leads 2-meter temperature equal, near surface equilibrium temperature gradient variability. And when it comes to SF, synoptic scale at heat flux regression, it shows large positive regression at positive legs. That means equilibrium temperature gradient leads synoptic scale at heat flux growth or suppression. Okay, then what about upper level temperature gradient? So upper level temperature gradient also shows large enhanced PF. Not also, sorry, it's contrasting. So it's more effective in driving PF. And for the synoptic scale at the heat flux, it also has large magnitudes, but they cancel each other if you kind of average over the negative and positive legs. So it has kind of relatively smaller impact on synoptic scale at the heat flux between the upper tropospheric temperature gradient. Okay, so the last part is a zonal Q gradient. So zonal Q gradient is mostly responsible for PF increase, but it turns out it is also preceded by this negative regression at negative legs. So there is a kind of cyclic behavior. Then we can further ask, oh, so zonal convective heating. So convective heating is independent of flux gradient relationship, and also it has a 30 to 40-day periodicity. Then is there any physical phenomenon to explain this cyclic relation between convective heating and the eddy heat flux? Then actually there is, which is Madden-Julian oscillation. So we further investigated if Madden-Julian oscillation is related to this convective heating asymmetry. So we did lag correlation between the real-time multivariate MJU indices and the Q index. And so 7 days prior, 7 to 10 days prior to this negative regression between Q index and PF, we found that zonal Q asymmetry is suppressed, because phase 1 and phase 2 implies that the zonal convective heating asymmetry is suppressed. And near lag day 0, there's a MJU phase 5, phase 6 related to this Q index. That means zonal Q asymmetry is enhanced around lag day 0, and that leads to the PF increase. Yeah. So we found that this zonal Q index relationship between against PF is at least partly driven by Madden-Julian oscillation. The last result of this talk is the DJF time series of the 3 indices over the recent 40 decades. So there is obviously a declining trend of surface equilibrium temperature gradient because of Arctic amplification. That's well shown here. However, unlike what future projections of climate models expect, there hasn't been yet this increasing trend of upper tropospheric equilibrium temperature gradient, because Arctic polar is also warmed pretty much as comparable as tropic does. So there's a muted trend of upper tropospheric equilibrium temperature gradient. However, when it comes to Q index, there's an increasing trend of zonal asymmetry in tropical convective heating. Yeah, and that's, if you look at more closely, then we see that this is precipitation product, GPCP, ER5, and generally convective heating. We can see that they all share the common spatial features, and that's corresponding to this enhanced zonal asymmetry of tropical convection over the tropical Pacific for the recent few decades. This is not only for precipitation, it's observed from sea level pressure, outgoing long-wave radiation, sea surface temperature, or vertical velocity. So it all indicates that there's a La Nina-like trend, strengthening worker circulation observed over the recent few decades, which is not simulated at all by climate models. So summary of this talk, so corresponding to the weakening trends of this equilibrium temperature gradient, synoptic scale at heat flux shows declining trends in both Boreal summer and winter, but not in March. I'm not sure why. So the follow-up study will be merited for understanding what happens in March. For Boreal summer, the high latitude land warming due to shortwave radiation anomalies is a main driver of weakening this equilibrium temperature gradient, and thus Synoptic-Scale Eddy flux in the latitude. For Boreal winter, I'll invite Planetary-Scale Eddy flux here. It's playing an important role in Arctic warming. That's not what community mostly think, but I think it's Planetary-Scale Eddy flux is really important because they regulate the equilibrium temperature gradient first, which leads to the Synoptic-Scale Eddy flux decline. Yeah, so this is the end of talk, and thanks for your listening.
Okay, any questions?
Yeah.
Kamsima, I think you got your hands up a bit quicker.
So let's go to your slide 19 and the point. Could you, this is just a clarification. I didn't see the magnitude, I just saw the colors.
Yeah, sure.
What the magnitudes are.
Magnitudes. Oh, okay. So I didn't bring the color bar here. Magnitude, we converted this Eddy heat flux by multiplying air density and the heat capacity CP, basically. So it's not Kelvin per meter second. It's usually the Eddy heat flux unit is Kelvin per meter second, but we convert it to watts per meter square by multiplying this constant. So it's not usual.
So the scales are the same then?
Yeah.
For the planetary. And
Yes, they are same. They are same.
so in your conclusions for part 1, you have this, you have 1.7 degrees centigrade for land warming and 1 degree for ocean warming.
Yeah, that's not. Yeah, my colleagues will. Yeah. But this is global, by the way. Yes, this one.
Yeah, and from how you presented it, and maybe I got it wrong, it seems to be that the 1.7 is more significant, but I would say given the heat capacity of the ocean, I would say it's the reverse, isn't it? It's the ocean which would be important because the difference of 0.7 degrees is not compensate for the.
Oh yeah, I'm not saying that. Yeah, ocean warming 1 degree is not that important. It's they are obviously both important, but the degree of land warming is getting larger over the recent decades. So I just wanted to make a point that we need to focus on this land warming as well. Yeah, I'm not saying ocean warming is weaker, so it's not that important.
Okay.
So Minghua, you have a question?
Yeah, so for the
Yes.
variability
In
the summer, you showed that it's the solar radiations that leads to warming in the high latitude, then the
Yes.
reduction of the synoptic eddy transporter.
Yes.
So what can you explain the changing of the solar radiation? Is that a random thing or?
That's really a great question. Yeah, that's really a great question. We didn't address that point in the study, but I assumed the more solar radiation is due to less clouds, less low thick clouds over this Eurasia region. And then the question is there an interdecator trend over this clouds over the Eurasia? Because I'm linking intraseasonal variability to interdecadal variability. Then I'm not sure if there's a trend, interdecator trend in the cloud products. But I assume it's related to the cloud. Yeah. So the short answer is I assume. I didn't. Yeah.
Brian?
Actually, I had a similar question.
Yes.
So I was wondering about the role of cloud versus snow cover, which, I'm not sure when the snow melts there, but, at least as you get higher up north of 60, I imagine there's some some snow as you head into May and June.
Uh,
So then I was wondering,
Mhm.
in the future, right, if there is less snow cover and then that whole summer pattern or change may vary, you know. And also if the ground heats up or the fluxes are different, then the low clouds may change too, obviously. But it seems like it's a moving target, right? Because whatever trend we're seeing now may not be the same in the future if snow and ice cover are retreating. Perhaps.
yeah, I agree. Yeah.
But I wasn't sure if it was clouds or
Yeah.
things going on.
Yeah, I'm not sure either. Probably looking at the cloud products will answer the question. Yeah, that's a great point. So, and also I want to point out that these are all observational results. So I'm not sure what climate models are doing with this, my proposed mechanism here.
So I actually have a question. So you showed some results that suggest, some modeling results that suggest that the upper tropospheric temperature gradient is more important in controlling the Eddy heat flux. So, but your observational or your reanalysis analysis is different. So, but is that sort of I was wondering, is that model result a sort of robust result? Because it depends on on your mean flow,
Yes,
your state of the atmosphere.
I agree. Yeah, it's not. So model results of this testing, the sensitivity actually vary. Depends on how you set up. Actually, also it's dry model, so it's pretty different from the real world. And this study, I didn't show that their follow-up study used the climate models to test this idea. And in their climate models, it's lower troposphere temperature gradient that drives Eddy heat flux decline. It's not upper level, it's lower level temperature gradient change. So our study, the purpose of our study was actually suggesting observational evidence. So many studies focus on idealized models, climate models, but that's not what real world is showing. So we want to add observational evidence or observational results that the upper level temperature gradient is capable of driving this planetary-scale heat flux, but because of its muted trend, we don't think upper level temperature gradient is playing a role. Yeah. We think zonal asymmetry of tropical convective heating is playing an important role. So for climate models, I think, or idealized models, yeah, your point is right. It's hard to say with confidence.
Other questions? So other questions from the oh well, I think most people have logged off. So yeah, okay. I think thanks again.
Thanks
yeah,
again.
thanks to Peter again.